In this video, we're going to talk about section 2.1 from our textbook, and that is the introduction to limits. And we'll actually start off with looking at the following example. So suppose we have a function f of x is equal to x plus 2, and what we want to do is discuss the behavior of the values of f of x when x is close to 2. And so we have this graph here, and what we want to do is see what's happening with our output values as we get closer and closer to 2. So let's say we're getting close to 2 from this side. So we can start from -2 to 0 to 1 to 2. And we just want to get closer and closer to 2 and see what's happening with our output values. And as you can see, as we're getting closer to 2 from this side, our output values are getting closer and closer to 4. If we were to look at the output values, look at f of x, as x gets closer and closer to 2 from this side, so from 4 to 3 to 2 and getting super close to 2, we see that all of our output values are getting super close to 4. So this tells us that the limit of our function as x gets closer and closer to 2 is equal to 4, and we would write that like this. So the limit of f of x as x approaches 2 is equal to 4. Alright, so this brings us to our formal definition of a limit. So we write this. So again, the limit of f of x as x approaches some value c is equal to L. Or we can write that as f of x approaches L, f of x approaches L as x approaches c. And so c is some number that x is going to get close to but not equal, and it's going to get close to c on either side of c. All right, something to note here is that the existence of a limit at c has nothing to do with the value of the function at c, and we'll see that in a few examples. So let's look at this problem here. So we are given the graph of h of x, this function here, and we want to find the limit of this function as x approaches 2. So something to note here, we have our absolute value function. So when x is less than 2, our function h of x is going to be equal to -1. So for example, if we were to look at h of 1, we get 1 minus 2 over the absolute value of 1 minus 2. This is -1 divided by the absolute value of -1, which becomes -1 over 1, and we get -1. And you can do this for any value less than 2. Absolute value of -4 becomes a -4 over 4, and this is equal to -1. So this is the case whenever x is less than 2. And on the other hand, when x is greater than 2, h of x is equal to 1. And we do the same thing, we can plug in some values, and we'll see this. And the graph actually displays this for us. So if we look at all the values of x that are less than 2, our h of x is equal to -1 here. And if we look at all the values of x that are greater than 2, our h of x is equal to 1 here. All right, so this actually tells us that the limit of h of x as x approaches 2 does not exist. And we can abbreviate this as DNE. And we'll come back to this in a moment. So let's first look at the definition of one-sided limits. So this is our notation. We'll write the limit of our function as x approaches c, and there's this minus sign up here. So that just means from the left, and that'll be equal to k here. So this notation here is read as x approaches c from the left, and we call this limit k our left-hand limit. Similarly, this is our notation for if x is approaching c from the right, and this limit L here is called our right-hand limit. Now, something to note here, if no direction is specified, we'll always assume that the limit is two-sided. And with that being said, Theorem 1 here talks about the existence of a limit. So in order for a two-sided limit to even exist, the limit from the left and the limit from the right must be equal. So this is written out. So the limit of our function as x approaches c is equal to L if and only if the left hand and the right hand limits are both equal to L. So coming back to this example up here, if we approach 2 from the left, we get the limit is equal to -1. And if we were to approach 2 from the right, we get that h of x is equal to +1. So this means that the left hand and right hand limits are not equal, and so that's why we concluded that the limit does not exist. All right. Let's look at another problem. We're going to do the matched problem 4, so you can look at example 4 in the text, and we're going to do something very similar here. We're going to use this graph here to answer A through C here. So let's start out with A. We want to look at this graph and study the behavior of f of x for x values near 0. So what we'll do is we'll just look at the limit of our function as we approach 0 from the left and from the right and see what we get. So we'll look at the limit of f of x as x approaches 0 from the left. And looking at our graph here, as we're getting closer and closer to 0 from the left-hand side, we see that all of these f of x values are getting closer and closer to 0. So we'll say that this is equal to 0. Similarly, we're going to approach 0 from the right-hand side. So we're getting closer and closer to 0 from the right, and we see again that the limit of our function as x approaches 0 from the right is also equal to 0. So we can conclude, since the left-hand and right-hand limits are equal, that the two-sided limit as x approaches 0 is equal to 0. All right, and then lastly, we'll look at the value of our function at x equals 0. So if we were to plug x equals 0 into our function, which looks like this, we do see that we get 0 back. All right, so let's look at B and do the same thing. We want to look at the behavior of f of x for x getting closer and closer to 1. So again, we'll look at the limit of our function as x approaches 1 from the left, and the limit of our function as x approaches 1 from the right. All right. So approaching 1 from the left, we're moving this way. We see that our output values are getting closer and closer to this value here, which is 1. And then approaching 1 from the right, so we're coming this way, we see that our output values are getting closer and closer to 2 here. So since our left hand and right hand limits are not equal, this tells us that the limit of our function as we get closer and closer to 1 does not exist. And then we'll also see here that plugging in 1 into our function is not defined here, because these open circles here tell us that we are not defined at x is equal to 1. So we're undefined there. And then lastly, we will look at part C. So we want to look at our function for x near values getting closer and closer to 3. So if we were to do the same thing, and look at the limit of our function as x approaches 3 from the left and from the right. So approaching 3 from the left, getting closer and closer to 3, we see that all of our f of x values are getting closer and closer to 3. And then approaching 3 from the right, so coming this way, we see that again, all of our values are getting closer and closer to 3. So that's nice. This tells us that our limit does exist, and it's equal to 3. And then lastly, looking at our function value at 3, we again see that f of 3 is not defined. And that's fine here. So something to note here is that the value of a function at x is equal to c is going to have no effect on, on the limit of our function as x approaches c. And I think that was said above in our definition of a limit, but I just wanted to reiterate that. All right. So we have this big theorem here, which talks about the properties of limits. I'm not going to read through each one, but we'll see in the next examples how they can be used. And then theorem 3 here is very important for polynomial and rational functions, and it tells us that the limit of our function as x approaches c is going to be equal to the value of our function at c for any polynomial function. And then the limit of our function as x approaches c is going to be equal to the value of our function at c for any rational function as well that has a non-zero denominator at that value c. Okay, so what we'll do is just go through a few examples to demonstrate this. So let's look at A here. And I'm just going to rewrite this so we can... Okay, so we want to find each limit. And the first thing that I'll do is I will rewrite this using the properties of limits above. So essentially what we can do with these limits is, in a sense, distribute them to each term here. And this is because of these properties here. If we're going to take the limit of the sum of two functions, that's the same as taking the sum of their limits. And same here, if we were to take the limit of the difference of two functions, that's the same as taking the difference of their limits. So this can be rewritten as like that there, and then we can take each individual limit. And remember, for any polynomial function, which this is, the limit of f of x as x approaches c is equal to the value of our function at c. So what we can do here is we can just plug in -1 into x, wherever we see it. And then another property here is that if we're ever taking the limit of just some constant k, that's just going to be equal to k. So the limit of 3 as x approaches -1 is just equal to 3. All right, then we know -1 to the 4th power is 1, and then we know that -2 times -1 is 2. So we get 1 plus 2 plus 3, and we get 6. All right, looking at this next example, B, we have a square root function. And what we'll do first is rewrite this using two different properties, the first being property 8 here. So if we're going to take the limit of a root function, then we can just take the root of the limit. So that can be rewritten as that there. And then again, we can distribute this limit. So this becomes the square root of this guy here. And then just plugging this in, we get the square root of 3 times 2 squared minus 6. And this ends up being the square root of 6. All right, and then lastly, we'll try to find the limit of this function here. So we have x squared over x squared plus 1 as x approaches negative 2. And then another property we can use here is property 7 here. So if we're going to take the limit of this quotient here, we can just take the quotient of each individual limit. So this becomes that guy here. And then again, we can just plug this right in. This is a rational function here. So and we get 4 over 5. All right, so not too bad. We can just use these properties here to find these limits. All right. So something else that I did want to bring up is indeterminate form. So if the limit of our function is equal to 0, and we have a rational function here. Okay, we're going to restart. Okay, so something else I did want to bring up is indeterminate form. So if we had a rational function here, and the limit of our f of x is equal to 0 and the limit of our g of x is equal to 0, we have what's called indeterminate form. So pretty much just 0 over 0. And this is important and will come up in a bit. And then I also wanted to bring up theorem 4, the limit of a quotient. So if, excuse me, if we have that we have a rational function here, and essentially the limit of the numerator is equal to some number that's non-zero, and the limit of the denominator is actually equal to 0, then the limit of this quotient does not exist. So we'll look at a few examples to illustrate this. Let's look at this first one here, a. So if we want to take these limits, we know that a can be rewritten as this here, just from our examples above. And then we again know that we can just plug in our value for x. So then we end up with 2/3 here. So this limit here is not in indeterminate form, and it does exist, and this is what it is. Now looking at example B here, we again can rewrite this. And plugging this in, plugging 3 in, we get 3 minus 3 over 3 squared plus 9. And this is 0 over 18. And 0 divided by anything is just 0. So that is our limit. So we're good there. And then lastly, we'll rewrite c we can again plug in our 3 here. Now in this case, we get 9 minus 9 on the top, so that's 0, and 3 minus 3 on the bottom. So this example is in indeterminate form. Alright, so the last thing we will talk about in this video is the limit of difference quotients. So we want to let the function f be defined in an open interval containing some number a, and one of the most important limits in calculus that we'll see is the limit of the difference quotient, which is given by this here. So this here is the difference quotient. So if the numerator here is equal to 0, then this limit here will be in indeterminate form. And we'll learn more about the difference quotient as we move along in this course, but I did want to just bring it up and show you guys how we can find the following limit. So we want to find the limit for this difference quotient given of our function f of x here. So first, what I'll do is I'll figure out what the numerator is. So f of 4 plus h. So all we got to do here is plug in 4 plus h wherever we see an x in our function. Simplifying this, we get alright. And then we also want to figure out what f of 4 is. So again, just plugging this in wherever we see an x. 7 minus 8, so that's negative 1. Okay, so with this information, we'll find the following limit. All over h. Okay, so now it just comes down to doing some algebra. We have positive 1 here. H is still on the bottom. Minus 2h over h. So our h's cancel. And we're left with negative 2 is our limit. So again, like I said, we will see the difference quotient later on in this course, but I did want to just leave this here with you guys for now. Okay, so that's it for this video.